through there. This is a very felsic rock with almost no iron in it. It's like a rhyolite for the dike. We can see no veins in here. The veins just absolutely stop on that contact because this rock doesn't break. It's sliding. We see both these rocks break. We can see the vein is refracted across the boundary. This rock is ore. It's gold ore because it's got iron in it, and all these rusty things are sulphide. So that bit there probably goes 10 grams per tonne, something like that. This is not ore, it's veined, but there is no iron, it doesn't react with the fluid, you don't get any gold out. So that's waste, there's the ore. You can see a beautiful example of selective failure of these units, and then selective reaction. Even though this rock has failed, it hasn't reacted with the fluid because it doesn't have any reactants in it. So that's what I would consider a classic outcrop showing these features. Now we come to a Moore circle. If you can't understand this, yell out Phil, Phil, because he'll come and explain it to you. In a very simplistic form, I hated Moore circles when I was a student, never could understand them properly. But in a very simplistic case, the diameter of the circle, so we can see there's a circle there, or that circle there, or this big one over here, is the difference between sigma 1, which is the maximum stress, and sigma 3, which is the minimum stress. Right? So if you've got a big stress, something is got a major stress, it'll have a big circle. If it's got a small stress, it'll have a small circle. That's very simplistic. If there's a high fluid pressure, it will drive the circle over in this direction. Now we've already said that we know that it's low pressure here. The sigma 1, sigma 3, sigma 2, there's not much difference, there's not much movement. So we've got a very low pressure, low difference between the maximum stress and the minimum stress. So we know we're in this sort of field down here. We're not in this one out here. We're in one of these down here, where we've got a very small, diameter circle in here. Now that line there represents the tensile strength of the rock. If this circle touches that, it'll break the rock. If it doesn't touch it, it won't break the rock. If it goes over, we've got a very large stress, it could go over that line and break a whole lot of rocks. Now we've got a low rock, we've got a low diameter here. This is just a series of rocks. It's just a typical one I pulled out of the literature. So there's that's that line for those rocks down there, those rocks there, those rocks there, those rocks there. Now if we've got a very small sigma 1 to sigma 3, got a high fluid pressure, might move it that way, we can see that the Moore circle will just touch these rocks. So if we had all those rocks in the sequence, only those two would probably break, maybe that one. So the circle would be here, so it would be like this or like that. We'd only break those rocks and we wouldn't break any of those. So that's exactly what we want. We want one or two rocks to break and the other rocks not to break at all. We want to focus all our fluid through one rock. We can see this very, very clearly in some graded greywackies. Now these are just single units. So that's the bottom of a greywackie. These are boomer cycles. I don't know what you call them, but they're graded. So they go from grit or conglomerate through sandstone up to shale. There's the bottom of the next layer in there. This is sandstone again, and there's the shale at the top of the next layer. So these are just single rock units that are graded from conglomerate or grit up to shale. What you can see is this is perfectly displayed here. Although they're single rock unit, it's only the competent, it's only those rocks that have failed. In other words, we've got in a single rock unit, we've got this unit in here, we've got some unit with that tensile strength out there. This one fails and that one doesn't. So this one is failing, this one is not. You can actually see there are a few of these veins that are parallel. There's one very nice one up there, you can see it curving into the shale, because this is ductile, this is brittle under these conditions. So that's exactly what we want to form our ore deposit. We really want a brittle unit. We obviously don't want this one because it's very small. But if we imagine it on a big scale, we want a nice competent unit like a basalt or a dolerite or a banded iron formation surrounded by ductile units like shales, sedimentary rocks, ultramafic rocks or something like that. So this rock, this touches that one, it doesn't come across to the tensile strength of the other one. So, so that's what we want. If you look in Juneau, Alaska, for example, there are gabbro intrusions into sedimentary rocks. Gabbro intrusions look like that. The ore body is where these things hit the gabbro. All the sedimentary rocks just flowed around it. So this is a very common, that's the sort of situation that we need. Now, we can judge this just by looking at stratigraphic sections. If we know we're in a mineralised terrain, we want to find, we've got some idea about which rocks break and which rocks don't break. So here's a typical section. I didn't make the section, I just took it out of the literature, made a slide of it. So we've got a sedimentary sequence up here, overlying a volcanic sequence with some dolerite sills in the sequence. Now where is the biggest ductility contrast? There. If we want to find a strong rock against a weak rock, where is it, do you think? So in other words, we can start our prospectivity, we can start thinking about where in the stratigraphic sequence are we going to find the right rock contrasts. Anyone game enough to say? I'm sure. Pardon? Yeah, we could have, this would be one case. We could have the Kamalia is a weak rock and the basalt is a strong rock, so we could have it there. What's a stronger rock than a basalt in the section, do you think? Dolerite. So the strongest rock is actually a dolerite because the basalt will have tuffs and pillows and things. The dolerite's a really solid rock. It's coarsely crystalline. It'll be the most brittle rock in the sequence. And what is the weakest rock in that section? Shales and the argillite. So shales and the argillite. So where do they come together? They come together there, right? Guess where the Golden Mile gold deposit, which is 100 million ounces or something like that, I can't remember exact figure, it's exactly at that contact. Okay, and all the other dolerite hosted ones are down in this dolerite, which is nowhere near in as good a position. You do get shale against it because they're actually thrust against it. So some of this rock is thrust against this. Where that's thrust against that, we do get deposits. But the big one is actually there. So one of the things you can start doing is looking for sequences, looking for positions in your stratigraphic sequence where you think you've got these contrasts. Okay? And what I've noticed is that greenstone belts that have sedimentary rocks overlying the volcanics are 1,000 times better than ones that have early sedimentary rocks with basalts or volcanics overlying. Because there are some like that, they're very poorly mineralised because the brittle rocks are above the ductile rocks.
Maybe in Egypt, talk about Egypt, how you've got those Hammamat.
Huh?
You've got Hammamat sediments in Egypt above the
yeah.
volcanic.
And when we're in Egypt, of course, we've got sedimentary rocks above the volcanic rocks.